So informally, a limit is the intended height of a function. How high or low, as in the y value, of a particular function or graph or curve. The actual definition of a limit, it says a limit allows us to describe how a function behaves as the input approaches a particular value. We can solve limits algebraically, numerically, and graphically, and we will solve limits algebraically, numerically, and graphically. So the way you write a limit, as you can see right here, guys, limit as x approaches a being a particular input value. So as x approaches a particular input value of a, we're saying what is the limit of f of x being the function. So it's, again, the limit as x approaches a of f of x. So those three graphs you see right here, it says all these graphs illustrate the existence of a limit as x approaches c, but never depends on how the function may or may not be defined at c. You see, if I said what's the value of the first graph over here, and I say what's the value when x approaches 2, what's the value at x equal 2, you'd be like, well, it's an open circle there, so there's no value at x equals 2. Yeah, but there's a limit. There's an intended height of the value. I go to this one and say, okay, what's the intended height or the limit as x approaches 2 of this one? Well, the intended height is right there, but again, that's not exactly what f of 2 is. F of 2 is actually 2 in this example there. So here if I say, what is f of 2? You'd say, well, it doesn't exist, so non-existent. If I say, what's f of 2 here? You'd say, well, f of 2 is 2. And if I say here, what is f of 2? You'd say, well, f of 2 is 4. See where the purple dot is? So that's defined at 2. So f of 2 is defined there. Here at 4, here at 2, and it doesn't exist here. But if you look at each of these graphs, guys, the intended height is trying to get to be at 4. The intended height is trying to get to be at 4, and the intended height is trying to get to be at 4. Because as the graph, again, x approaches 2 from the left side and from the right side, they're all trying to meet at the same location at the y value of 4. As again, the graph approaches 2 from the left and 2 from the right, it's trying to get to 4. And as this graph approaches 2 from the left and 2 from the right, it's again trying to get to 4. Okay, so you can see on the bottom, function f has a limit of 4 as x approaches 2, even though f of 2 may not be defined at 2 every single time. So again, it's not defined at 2 here. It's defined, f of 2 is defined at y equals 2, and here at y equals 4. Alright, so a very quick first example here. It says using the TI, using your grapher, find the following limit. And again, this is just an example. We can find limits without using a calculator as well graphically. We can graph them out, but I'm just saying, here's an example of finding limits graphically. So you're going to basically put this in the calculator and find the limit as x approaches 0. When you do graph this, you're going to see that the curve is going to be what's called oscillating, and it's going to jump up here and then oscillating there as well. Now I'm off again, a little to the left, but you get the idea that the sine of x over x when you graph it is going to look like that kind of a curve. And so again, if it was more centered the way it should be, you can see that the limit as x approaches 0 is 1. And I want you to memorize that limit. Again, as x approaches 0, the limit as x approaches 0 of sine of x over x is 1. Pause the video. I want you to do each one of those and come back when you're done. I'm going to guess that if you did them all and checked and now started the video back up, you'll see that all the answers are 1. Again, if you're just letting this video play and just assuming that, okay, it's what it is, that doesn't do you justice. You need to throw these into the calculator and look at them. But if you did this, look at this and think about that first example we did on the previous page, where I said, hey, what's the limit as x approaches 0 of sine of x over x? It was 1. So, when I say memorize that pattern, that function, that limit, that pattern works with these examples as well. Again, notice what's happening. The x's, like, again, think of x being an angle measure, right? So, x over sine of x. These are the same angle size. 2x over sine of 2x. Hey, they happen to be the same angle size, like almost like double angle, isn't it? Think about that. And then 3x over 3x. and then 3x over 3x again. Now again, it's 3x over sine of 3x, but I want you to notice that these angles are the same. So if I said it was the limit as x approaches 0 of sine of 5x over 5x, you'd say 1. What's the limit as x approaches 0 of 21x over sine of 21x? You'd say 1, because it's the same pattern that follows each time. Now sometimes the value of a function tends to different limits as x approaches a number from opposite sides. So there are what are called one and two sided limits. So the first one here, it says the limit as x approaches c from the right. So it looks like an exponent of a plus sign. I got you, okay? That's just notation. It's just notation. So this means the limit as x approaches c from the right of f of x. Again, it says right here, the limit of f as x approaches c from the right. So the one underneath it, the limit of the function as x approaches c from the left. So when the exponent or the power is a plus sign, you're approaching from the right side. If the exponent or the power, again, looks like a minus sign, you're approaching from the left. Again, this is just notation. Please remember that. It's just notation here. But it's important notation to understand. Now, here's a super important theorem and or definition of limits. The LHL and RHL, that stands for the left-hand limit and the right-hand limit. So if the left-hand limit equals the right-hand limit, then the limit exists. Again, a limit, remember, is the intended height of a function. Again, when the left-hand limit equals the right-hand limit, that's when the limit exists. Let me show you again another example. So I'm coming in from the left, and I'm coming in from the right. My point is, both these curves, I know they're funky looking, but they're both trying to get to a particular height of the function, a particular y value. So the limit exists here as x approaches a magic number, we'll call it c. So the limit exists at that location right here, because the left-hand limit and the right-hand limit approaches the exact same height of the curve at a particular x value. That's where the limit exists. So you can't have anything like broken. Okay? Cool. Alright, so here's another example. We're going to solve by using the graph. We're going to find limits by using the graph. So the first example, A, says find the limit of f of x as x approaches 1 from the left. Again, notice the notation right here, guys. As x approaches 1 from the left. So this is where x is 1. You can see that, obviously. So they're saying what is the limit, what is the intended height of the function as x approaches 1 from the left. So coming in from the left, as x approaches 1, what is the height of the function? Right there. The height would be 5. That's the answer for the first example, A. Alright, so let's try the second example. Example B says, find the limit of f of x as x approaches 1 from the right. Now again, we're coming from the right side. So as x approaches 1 from the right, what is the height of the function? As x approaches 1 from the right, you find a height of 1. So there's the answer for question B. Alright, question C. Find the limit of f of x as x approaches 1. Now when they say it that way, they're intending from both directions. So the limit as x approaches 1 of that function. We're going from the left side and from the right side. So as x approaches 1 from the left, and x approaches 1 from the right. Oh man. You see how they're broken right here? How they're not the same value? You can even see it here. Not the same value. So if that's the case, if the limit of approaching from the left is not the same as the limit as it approaches from the right, that means the answer D, N, E, as in does not exist. The limit as x approaches 1 of this particular graph does not exist because of the fact that the limit from the left side and the right side are different. The left-hand limit does not equal the right-hand limit. Alright, so here's our fourth question. What is f of 1? Where is it defined? F of 1. F of 1 equals 2. F of 1 equals 2. Why is it equal to? Because again, I'm saying what is f of x particularly defined at? Well, if x is 1, f of 1 is 2. And you can see that dot right there. So we had talked about finding limits not just graphically, but algebraically. and numerically. So this one says determine a limit by substitution. Support graphically. Alright, so what they mean by determine a limit by substitution is basically doing it numerically. All this is, guys, literally all this is, and you can write these down if you want to. Again, all this is literally plug and chug. So they're saying for this example, find a limit as x approaches negative 3 of the function 2x squared plus 4x plus 1. You know that's a parabola opening upwards. So they're saying what is the y value or the height of this function when x approaches negative 3. So when I say literally plug and chug, and I mean literally plug and chug, all you're going to do is take a negative 3 and plug it into the x's in that function. So here we go. 2 times negative 3 squared plus 4 times negative 3 plus 1. Plugging and chugging away, what do we get? Negative 3 squared is 9. 9 times 2 is 18. Negative 3 times 4 is negative 12. So we have 18 minus 12. 6 plus 1, 7. That is the answer to the question. So the limit as x approaches negative 3 of this particular function, 2x squared plus 4x plus 1, is 7. That's it. Lovely. Now, if the limit cannot be found by direct substitution, as you can see right here, if you try to plug and chug with the 1, it's not going to work. Because again, if you literally try to plug and chug with this 1 here, 1 minus 1 is 0. Okay, that's no big deal. But then if you try to plug in the 1 here, 1 cubed is 1, minus 1 squared, which is 1. So 1 minus 1 is 0. Plus 1 minus 1 is still 0. Now we're dividing by 0. Can't have that. It's impossible. You cannot divide by 0. So, if the limit cannot be found by direct substitution, you can do some factoring to help find the limit. So let's do that. Oh, and again, support graphically. When I say support graphically, just like the previous example, you can then grab your calculator, throw the equation, throw the function into y equals, graph it out, and look. As x approaches that particular number, look at the height of the graph, and that proves it or supports it graphically. Alright, so for this one, we're going to factor. Here we go. Alright, so I saved us a little bit of time. So what I was doing here, guys, is I was doing a little squiggly method down here, or the grouping method, to factor this. So I did that and got the factors right here. Looking at the factors right there, then, I'm going to be able to cross out, which is sort of nice, boom and boom. When you cross out those common factors, that doesn't mean there's nothing in the numerator. There's still something up there. It's a 1, so we need to make sure we have that. So as we write down the next line, I want you to include the limit, literally conclude the limit as x approaches 1 in the next line down, as we're going to write this, okay? So that's what I mean when you write this down. I want you to include the limit notation. Limit as x approaches 1 of 1 over x squared plus 1. Now plug and chug and see what happens. So if you plug and chug the 1 here, we have 1 squared, which is 1 plus 1, which is 2. So we can answer this question now. So the limit as x approaches 1 is 1/2. There it is. And once again, you can prove this supporting it graphically. What I would do is probably take the original function, make sure you group the numerator and denominator as you throw it into y equals, and graph it out. And then notice, again, as x approaches 1, the y value will be 1/2. Alright? Sweet. As you guys get into the chapter on limits, you're going to have to learn these properties and work with these properties. So take some time to look them over. Alright, thanks for watching.